the subject of this lecture is to introduce a new kind of integration to you. We're going to learn how to integrate over curves and lines in space. Okay? In particular, we're going to look at a so-called path integral or a scalar line integral. So that's the main idea of today's lecture, to learn about these path integrals, learn how they're useful, and also be able to evaluate some of these special integrals. Okay. All right, so like I said before, these line integrals allow us to integrate over curves in space. Okay, so for example, at school, what you've learnt, let's say you have, say, a function y equals f of x, and you want to integrate that function over the interval a to b. You're integrating over a special line segment there that lies in the xy plane. That lies in the on the x-axis. Now there are two kinds of line integrals. Okay, so you know what you already know involves integration over this little line segment, and that line segment lies in the x-axis. Now today's lecture is all about so-called path integrals. So basically, we are going to learn how to integrate scalar valued functions over curves like a helix or a semicircle or something like that. Some curve that sits in space. You've got some function that's defined on that curve. It'll take real values. How do you integrate over that curve? The other kind of line integral is line integral involving vector fields. And this is, we'll talk about that in another lecture. Now, one of our important applications of today's lecture with path integrals is calculating the total mass of a thin wire. So suppose the function is like a density function, and you know the density at each point in your wire. And that wire covers some sort of curve. Well, to calculate the total mass, what you do is you integrate the density function and it gives you the total mass of the wire. And we'll look at some of those applications today. Okay, now just to refresh your memory, suppose I have a vector valued function of one variable. So the boldface R just means a vector valued function and the t is the independent variable. When we say that this vector valued function R parameterizes some curve, curly C, basically what we mean is that the image of R traces out the curve. So, you know, let's just say I'm working in the xy plane here, and this is my curve C. At each point on that curve, you can form a position vector. Okay? Now, for the t values between a and b, let's say, you know, this point's corresponding to the point t equals a, and this point corresponds to the point t equals the value t equals b. What happens with this particular vector function is that as t increases from a to b, the vector will sort of move around and trace out that curve. And we looked at this in the very first lecture of this course. Okay? And one of the reasons why I put it in the first week of lectures is because when students get to this part of the course, they're overwhelmed by just the parameterizations. Okay? Putting the parameterizations in week one gets it in there really early. Really early. So you've had at least 3 weeks to think about parameterizations. Now you can see this curve here. Anyone remember the name for this curve, this blue curve? It's a helix, right? Think of it like a spring, okay? And we learnt how to parameterize, or give one parameterization for that spring using cosines and sine and t. Now, let me remind you that there's more than one way to describe a curve using a vector function, okay? You can parameterize curves with all sorts of different vector functions. Can anyone think of a different parameterization for that helix instead of this this representation? Anyone? Oh, in terms of t, in terms of a vector valued function of one variable. Anyone? No? Well, I'll let you think about that for a while. Okay, so in this context, line integral is, I really will speak of a path integral sometimes to distinguish them between scalar valued functions and vector valued fields. Okay, so suppose I've got some curve, curly C, let's just draw it in the xy plane. And I've got a function, say of 2 or 3 variables, and I want to integrate the function over that curve. And this is the notation we would use. Notice you've got a ds here, and you've got this c here. So this is like the general notation for a path integral. To actually evaluate it, you find a parameterization for your curve curly C. So in other words, you come up with some vector valued function that describes the curve C. You make a little bit of a substitution by replacing x with g of t, y with h of t, and z with k of t into your f, so it's all a function of t now. And you replace this ds, this is the so-called arc length element, with the magnitude of the derivative of your parameterized your parameterization function r. You replace it with the magnitude times dt. Now usually when I speak about magnitudes I put these double lines in, so you might just want to sort of put that in there if you want. Okay? So essentially that's the basic computation. That's what how we can evaluate these path integrals just using a parameterization. So let me just refresh your memory there. It all starts with the function f curve that you're integrating over. You've got to describe that curve in terms of some vector function r of t. But not any vector function will do. What we want to do is find a smooth parameterization. Anybody remember what a smooth parameterization is from almost? The derivative's continuous. So the derivative of r is continuous and never zero. That's what we mean when we say a smooth parameterization. This function here has a derivative that is never the zero vector, and the derivative is also continuous. That's what we mean when we say a smooth parameterization. Okay, so let's look at a special case. If my f is just the constant function 1, then this scalar line integral, or the path integral, gives us the length of the curve C. So if I just replace 1 in here, then that's just the arc length, or the length of the curve C. And this was discussed right at the end of first year, actually, but I'll refresh your memory a little bit today about that. Okay, so this, writing this in terms of my sort of function of t up here, you can show that the following is true. Essentially, the arc length is just the integral of this magnitude of the derivative vector from t equals a to t equals b. Okay, now this was shown to you right at the end of first year math 1231, 1241, but we didn't use the vector notation there. Okay, and if you want to look up the derivation for that, then I've got a video online that I'll link to actually show how the arc length is this. All right, well, how does this come about? Well, like most integrals that you've seen, they're all Riemann sums, right? They're the limits of Riemann sums. So you just slice up and you sum. Okay, so suppose this is my curve C. I slice it up, and in each little section, I choose a sample point. Okay, so you can see in this section, I've got a sample point. Now, each of those little sub-arcs or sub-curves will have a length, which I'm going to denote by this delta S sub k. Okay? All right. So what I do is choose a sample point in each sub-arc or sub-curve. I multiply the value of f by the length of each sub-arc, and then I sum them up. Okay? If you want to have some sort of physical interpretation of what's going on here, think of the blue line as a wire and f as a density function. Okay? Essentially what you're doing there is you're multiplying the density at the sample point times the length of the little sub-arc and adding them all up to give you an approximation to the total mass of the wire. Okay? So I can form my Riemann sum and then let n go to infinity, right? So basically you're slicing sort of widths go to 0 here. So we obtain this, this is like the limit of this Riemann sum. Now, like I said before, and you might not have this bit in your notes, it can be shown that a curve with a smooth parameterization R of t between, say, t equals a and t equals b has arc length this. Now, if I form, say, an arc length function just by replacing b with t, this will be a function of t. So what I can do then is just take the differentials of both sides, so a ds over here, use the fundamental theorem of calculus, differentiate here and use the fundamental theorem of calculus to get this. Okay, so how does that help us? Well, who knows how to evaluate this? I can replace ds with this and replace x, y, and z with your parameterized functions. So you actually get everything in terms of t. Let me show you what I mean with an example. Probably the best way is to look at an example to see what's happening here. This is an example of a path integral or a scalar line integral. Our curve, curly C, is this line segment here. And we're told that actually it's from the origin to the point 1, 1, which will just lie in the xy plane. Okay, so that's your C. What we're asked to do is integrate this function over that curve. Now notice the curve doesn't lie in either on the x-axis or the y-axis, so it's something that we haven't really seen before, like we did at school with those kinds of integration. Okay, so what we're going to do is firstly parameterize the curve C. So how do I parameterize a straight line segment from one point to another point? Well, I did talk about this in the first lecture. Okay, so a little bit of notation first. So let this be A and this be, say, point B. So OA is just the 0 vector and OB is just the vector 1, 1, right? Just position vectors. Now, how do I parameterize a straight line segment from sort of one point to another? Well, you can do it a lot of ways, but essentially this is the way that I think is the simplest. Okay, essentially if you have the position vectors of 2 points, you can introduce this independent variable t and just have 1 minus the starting vector, 1 minus t times the starting vector plus t times the finishing vector or the end vector from t equals 0 to 1. To me that's the simplest, okay? So if I replace OA with 0, the vector 0, 0, this is just going to be 0, the 0 vector. If I replace OB with 1, 1 and multiply each of the components by t, then actually I'm going to get this. So this is my parameterization. Okay, if you want to write it in terms of I and j, you can, no worries. Now, what now? Well, I've still got to do a couple of things. I want to evaluate f along that parameterization, and I want to calculate the magnitude of the derivative. So, along the curve C, what is going to be this? Well, essentially I just go up here, this is my f, I replace x with t. I replace y with whatever's here, t in this case. So it's going to be just t. And again, you know, we've got t between 0 and 1 here. All right, so I still need to calculate r dash. So to calculate, I just go to each component and calculate the derivative with respect to t. So if I differentiate the first component, I'm going to get 1. And if I differentiate the second component, I'm going to get 1 also. So the magnitude, I square each of these components, add them together and take the square root. So it's just... So for this particular curve, the tangent vector, r dash, has constant magnitude. That's not always the case. Sometimes you'll get the magnitude involved in t. But in this case, it's just root 2. So let's put it all together. We've got our elements. This is just... So we're integrating, this would be my A, 0 would be A, 1 would be B. So let's just write this out. And if I replace everything and form my integral, so f of r is just t, the magnitude of r prime is just root 2. So as you can see, I get a really simple integral to actually evaluate. Okay, so this bottom line now is it's just a regular integral, function of one variable. Okay? So it's pretty easy to knock over. So I'm going to integrate to get half t, basically a half here. So, well, I guess I can write it like that. Okay, so notice there are some definite steps with that particular problem. Parameterize the curve with a smooth parameterization. Calculate the value of f along that parameterization, along the curve. Calculate the magnitude of the derivative, multiply them and integrate. Now, in this particular example, if you think of a particle moving along the curve C from here to here, there's sort of like a direction. Down here we say, does anything happen to the path integral if we say change the direction? So I start here and I move that way and I integrate that way. What do you think? Does it matter about the direction?
Yeah.
Who thinks it does? Hands up. Who thinks it doesn't? Okay, who's not sure? Okay, well, the answer is it doesn't matter. The direction is not important. And I'll tell you why. Because it's the magnitude in here. So it doesn't matter which way the tangent vector is pointing. You're only concerned with the magnitude. Okay? When we look at vector line integrals, the direction is going to be very important. Very important. But for these scalar path integrals, the direction is not the direction of sort of travel, if you like, along, or the direction of parameterization along the line is not important. Okay, let's have a look at another one in 3D. Here we've got our helix, and the nice thing is the parameterization is given to you. So that's quite nice. We're asked to calculate the following path integral. So you can think of these components. So x, the x component is a function of t, y is a function of t, z is a function of t. My a and my b, my limits of integration, are going to be respectively 0 and 2 pi. So to calculate my line integral, first of all, I've got my parameterization. I can do two. Let's just calculate the derivative first. You don't have to. We can do it the other way. So I differentiate the components with respect to t. So cosine, that's going to go to minus sine. Sine's going to go to cosine, and t is going to go to 1. Now, of course, that derivative is never the zero vector, so it's a smooth and it's continuous. It's a smooth parameterization. So let's look at the length or the magnitude of this sort of tangent vector. So we square each of the components, add them together and take the square root. So sine squared plus cosine squared equals 1. So I'll get another one where actually the magnitude of the tangent vector is constant. Again, that's not always the case. It's not always the case. Okay? So physically, this would be a tangent vector to the helix. So along C, f evaluated along our parameterization for C is going. So that's our f. So it's going to be replace x with cosine, y with sine, and z with z with t. So it's going to be cosine t plus sine t plus t. So now what we want to do is take these two, multiply them together, and integrate with respect to t. So our limits of integration are 0 and 2 pi. Our f of r is here. Our magnitude of our tangent vector is root 2. And so I just want to integrate here. Okay?
That second last line is if outside of R.
Okay, r is a function of t. F is acting on r of t. No worries. Okay, so now it's boiled down to a reasonably simple integration. Okay, in fact, you can do these things using inspection, right? So integrate, what's the integral of cosine over 0 to 2 pi? 0. Sine, 0. So you only have to do one integration, right? The areas cancel each other out. So if you look carefully, sometimes you can save a lot of time. So the integral of cosine from 0 to 2 pi is 0, integral of sine from 0 to 2 pi is 0. So essentially, you just have to integrate t. So if I integrate t, I get a half t squared. So if I cancel that off, you're going to get something like 2 root 2 pi squared. Okay, so you can see, hopefully, you can see that there's a definite structure to the solution method for each problem. Parameterize the curve, describe it mathematically using your r function. Here it was given. Compute the tangent function, the r prime, and look at its magnitude. Look at the value of f along the curve, multiply everything together and integrate. Any questions so far? Okay, so to put this into some perspective, let's say the helix involved was the, let's say it was a spring or a coil, and the f was, say, a density function, right? What you've produced there is a measure of the total mass of the coil or the spring. Now, if this path integral is a kind of integral, what properties does it have? Well, firstly, let's say I've got two curves here, and say, I start here and I move along here and then I go up here, right? So I'm moving from this point to this point via these two sort of subpaths. To calculate the path integral, do I just integrate over C1 and integrate over C2 to get an atom together? Well, yes, you can. But the line integral is dependent on the path that you choose. It depends on the curve. So even though ultimately I get from the origin to 1, 1, 1, and in this case the origin to 1, 1, 1, I'm taking different paths to get there. So you would expect the line integral for these two situations, for some given f, to not necessarily be equal. Okay, they might be equal unless special conditions are satisfied. Path integrals are sensitive to the paths that you take. Okay, even if you end up at the same points, like in this case, the paths are sensitive. The path integrals are sensitive to the paths. Okay, unless there's some very special circumstances. Okay, so that's how to compute. Oh, actually, let me go back for a second. We're going to look at some applications, but before we do that, let's have a quick look at the geometric interpretation, a geometric interpretation of what we've calculated. Okay. Now I've mentioned total mass of wires and coils and things like this, but in this particular example, it's actually even simpler than that. Let me explain. This function here, it's a function of two variables. Think back to our section of function of two variables. What will the graph of x plus y all over 2, what will that represent? What is it? What kind of surface is it? It's a plane, yes. Okay, it's a plane. Now, this blue line in this picture, this is the part of the plane, the graph of this, that lies directly above our curve C. Okay, so this blue line lies above this curve C. I guess, you know, if you had C in a plane and you sort of intersected this with it, you'd get this blue line. Now, what have I actually calculated here? Can anyone see what I've actually calculated? Huh? Sorry? No, not quite. Oh, almost. Who said volume? Area, right? What we've actually produced in this, and this is why it's been drawn in, you've got this triangle. Okay? We kind of know that integrals give us area under curves. Now, we're integrating over this, and we've got this as our the part of that lies above. We can form this triangle. Actually, this will be the area of that triangle, or one side of that triangle, if you like. One sort of, you know. Think of that triangle as a fence. We've sort of calculated the area of one side of the fence there. Okay, so in real simple situations, you can think of these path integrals as calculating area, but you know, it's just for special examples like this. Okay, well, let's look a little bit more at more physical applications. Let's talk about the relationship of path integrals with total mass. Now, why are we interested in studying mass and centre of mass and things like this? Well, for a whole bunch of reasons that you could talk about for ages, but essentially, if we can locate the centre of mass, then of an object, then theoretically we can balance that object, okay, and keep it in equilibrium. Now, these path integrals provide a perfect vehicle for studying curves that lie in space and you know, springs associated with them. Okay, well, strictly speaking, when we talk about density of a material, it's the mass per unit volume. But remember, if we're working with say, thin wires or thin curves, we can't really measure that. So for wires, rods, etc., we're going to use mass per unit length. Mass per unit length. Okay? So you can, again, I've got the helix here. You can think of that blue curve as representing some wire. Okay. Well, we're going to use these path integrals to calculate the first moments of wires. We're also going to use them to calculate the moment of inertia, or the second moments. Now, let me show you the main ideas with respect to line integrals. Essentially, to calculate the total mass, where delta is a density function, you just compute the path integral of that density function over the curve. Now, there are some other ones here. The first moments about the planes and the centre of mass. Okay, so let's see how we can use this in a problem. Okay, so this is a good problem. It's fairly simple. We've got a wire bent in the shape of a parabola, and we've got a representation for the density function. Okay, we're asked to calculate the total mass of the wire. So, you know, it's just a basic example. Let's draw in our curve, and we're only interested in the curve between, say, x equals 1 and 4. Okay. Now I'm going to show you how to do this using path integrals. What we need to do, firstly, is parameterize that curve segment, that red line. Anyone have any idea how we can do it? Let's say using some variable t. Anyone? Yes, who said that? Who? Yes. Why? Why did you use t comma t squared? Correct. Okay, you can see here this is just a function of x. If under that condition, I can always choose a parameterization involving this. Okay? So let's parameterize c via t. So instead of f of t to be t squared, well, it is t squared. And again, t's driving here really, you could think of t as x if you wanted to. T is going to be between 1 and 4. Okay? So now let's compute the derivative and its magnitude, the tangent vector. So you differentiate each of these components and work out the magnitude. So again, square each component, add them and take the square root. Okay, I can't really do much with that at the moment. Okay, so along my curve, the density function is just, well, we replace y with t squared and x with t. So I can cancel off, I'll get t. And all I really need to do now is put those things together and integrate to calculate the total mass. So let's denote the total mass by m. This is the general expression that we're going to compute with. And all we need to do is just plug in. So here A is going to be positive 1, B is going to be positive 4. The density function along the curve is going to be t. And the magnitude of the tangent vector is this square root expression. Okay, so we've come down to some sort of integral that we want to evaluate. Sometimes these are easy, sometimes they're not so easy. For this one, anyone know, I mean I could just write it down, but anybody know how I would calculate that, the antiderivative of that, if I wanted to sort of justify it? Anyone? Well, if I look inside the square root sign, I've got 1 plus 4t squared, right? Inside the square root sign. And I've got a t that's multiplying. Now, if I differentiate 1 plus 4t squared, I almost get t. Okay? So I've kind of got a chain rule type, substitution type integration going on here. So if I wanted to do it formally, I would let u equal 1 plus 4t squared, right? I'd let u equal 1 plus 4t squared, then I'd calculate du dt, and it's almost that. Okay, so actually what I can do here, I'm not going to do that, I'll let you do that. Essentially, what I know is that the power of 1/2 here is going to go to 3 on 2. And all I need to do is touch up the front. Okay, so when I differentiate this, the 3 on 2 is going to come to the front, so I want to multiply by 2 on 3. When I differentiate, when the derivative of this, when that comes to the front, that's going to be 8t. So I've already got a t there, so I want to just divide by 8. Okay, so when I put in t equals 4 and t equals 1, and cancel out here, I should get the following. Oops. Okay, so this should be 65 to the power 3 on 2. Okay. I've shown you how to parameterize a curve in earlier lectures, and here we're using it to apply to some line integral calculation. Okay. Now, these are good questions. True, false. Suppose I've got a constant function, 5, and I'm integrating that constant function over a curve where I know the length of the curve. Say the curve length is 2. What will the path integral, the scalar line integral value be? 10. Who said 10? Who said it? Who said it? You. 10. Yes, you're absolutely right. Okay. Why? No parameterization necessary, right? So f, in this case, it's true. It's true that it's 10. Okay, so this is just 5. 5's a constant. I can bring it outside this integral sign. And what does this measure? What's this integral ds? That's the arc length. 5 times 2, 10. How good's that? Nice, huh? It'd be good if you got one of those in the exam. Okay, no parameterization necessary. All right, question 2. True, false. The scalar, so I guess up here I'm talking about scalar or path line integrals. Okay, it should be obvious from what kind of function this is. Is it a scalar or a vector? True, false. The scalar line integral does not depend on how you parameterize the curve that you're integrating over. Yes, it's true. Okay, as long as you use a smooth parameterization, it doesn't matter how you parameterize it. Okay, true. So let me give you an example. Let's take the unit circle in the xy plane. Okay, who can tell me a parameterization for the circle? The half circle from, say, this point around to this point. Yep, cosine t, comma sine t, where t, say, between 0 and pi. Okay? But I can parameterize this a whole bunch of ways. Let me show you another way. Cosine 2t, sine 2t, for 0 between t between 0 and pi on 2. Ah. Okay, they're two ways of parameterizing the same curve. What's the difference between them? Well, the second curve traces out, the second function traces out c twice as fast as the first function. Okay? So it does not depend on your parameterization. Okay, and lastly, a line integral, a scalar line integral is what I mean here. involving the function f does not depend on the direction that the curve C is traced out by the parameterizing function. True or false? It's true. Okay, it doesn't depend on direction. Doesn't depend on direction. Okay, and this is because essentially we're just looking at magnitudes of these tangent vectors.